Okay, so yesterday we learned about derivatives and integrals, and that's all very well and good. Maybe it'll help you in calculus, but why do we care for physics? So we're going to look very quickly at probably the most important thing about derivatives in physics. And we're going to start with a graph. But this time we're not doing some generic XY graph. We're going to use a graph that we've done in physics before. That is a position versus time graph, where position tells you your position relative to an origin, perhaps on a number line, maybe moving on a line, on a track, a cart on a track. It's only in one dimension though, and this is the time at which you're at that position. So we're looking at this. This is great. I can know some certain things, like if I asked you, where were you at time 2 seconds? Well, I can trace this up and go, okay, well, I was at position 2. That's nice. I guess if you need to know where to deliver flowers or something at a certain time, that's good to know. But there's something else we can get out of this graph, and it has to do with the slope. So I want us to look at the slope again. We said slope was rise over run, change in y over change in x, except for now we have x over here, so it gets very confusing. Let's say instead of change of y over change in x, we say is the change in the vertical axis over the change in the horizontal. In that case, that is the change in x divided by the change in time, which in this case, no matter what the numbers are, I'm going to have units of meters divided by units of seconds. Meters per second. Hopefully that will jog something in your memory. Meters per second is how we label speed. In fact, for a position versus time graph, the slope of the line is your speed at that time. On this graph, it's fairly simple because I have a nice straight line. The slope is the same everywhere, therefore we are moving at a constant speed. In fact, the constant speed was, well, I go from 0 to 4 and 0 to 4, so I have a change of 4 meters over a change of 4 seconds. My constant speed was 1 meter per second. But what if you have, like yesterday, a graph that is not a nice straight line? Could we find the slope and therefore the velocity from this graph? And the answer is yes. I'm just going to pause this for a second and draw another graph. Okay, and we're back. Here I have a graph of the position in height, and so I switched to y instead of x because we like to use y for vertical position and x for horizontal position, for a rock that's been dropped from rest. That is, I held it out and I let go of it. And it turns out when you do that, the equation for its position looks like this right here. I hope you can see the highlighted little mouse. It's right here, where g is the acceleration of gravity near the Earth's surface. That's 10 meters per second squared. So what if I wanted to know how fast the rock was falling at, say, let's just pick an x value. Let's say 3 seconds after I've dropped it. Well, I can figure out where it is by using this equation, plugging 3 in. I get 3 squared is 9, 9 times 10 is 90, half of that is 45, so it'll be negative 45 meters. So I'm going to go ahead and just throw that on here. I didn't put a scale on this, which is a very, very bad thing. I am naughty. Okay. So, what if I want to know how fast it was going? Well, from over here on the left, we know that the speed, or velocity, speed or velocity, it's velocity actually, because if we're going to get negative numbers sometimes, and that means direction, which means velocity. Velocity was the slope of this line. However, I don't have a nice straight line anymore, I have this curve. But yesterday we found out a derivative gives you the slope of any line, any curve, at a given point. So let's just find the derivative. The derivative will give us the slope. So I know that the velocity velocity v is going to equal the slope of this line, which is the derivative. Remember yesterday we wrote dx dy? This time we don't have x and y, we have x on the vertical axis and t on the horizontal. So the vertical axis goes on top, so it's going to be dx on top, and the horizontal axis goes on the bottom. That's going to be t. So what we have is that velocity is equal to the derivative with respect to time of a position. The derivative of position with respect to time. That's how you say this. You say derivative of position with respect to time. Get it? Yeah. The little line means with respect to. Sounds like you're addressing the court or something. Yeah. Anyway, in this case, for this velocity, oops, I'm using y instead of x, so we get dy dx, or oh gosh, dt. Why did I say that? I'm so sorry if I just confused you so badly. Okay. That's replace the y with what y equals. Negative 1/2 gt squared. Okay. And we do that polynomial thing that we did yesterday. I don't know if you remember it or not. You bring, oops, stop it. You bring the power of the variable, stop it, down in the front. So that's going to give us, I already had a negative 1/2, leave it, don't get rid of it. Now I've got this 2 down there in front. I already had the g, it's a constant, it doesn't do anything. But now I've got this t, and the exponent is the old exponent minus 1, this is t to the first, or just t. Well, these go away, blip. So I get that the velocity of the rock is equal to negative gt. That is the acceleration of gravity times whatever time you're talking about, whenever you want to know in this rock, the speed of what time. So I wanted to know at time 3. So at time 3, v equals negative 10 times 3, or negative 30 meters per second. I'm getting the meters per second from the labels on the graph. Meters per second. Meters per second. That's how fast the rock is going. And we can check that by thinking about acceleration from last year. Remember, acceleration is the change in velocity per second. We said that this thing was dropped from rest. That means that it started with a velocity of 0. If I'm going 3 seconds later, well, at time 0, the velocity would have been 0. 1 second later, it would have been negative 10. A second after that, so that's 2 seconds total, I would have added another 10 meters per second on the speed, and since it's down, it's still negative, so that'd be negative 20 total. And then another second, I add another 10 meters per second, so I have a total of 30. And there I am at 3 seconds, just like predicted.